Let's say you're doing some sort of calculation where you need to know the distance between two different places. It shouldn't make any difference in your calculation if you're told that distance in meters or in miles or in light years or whatever. If you're doing some sort of physical calculation, the results shouldn't depend on what units you use. It turns out that with data analysis, it is commonly the case that the units you use can actually influence the result. So principal component analysis has this kind of sort of flaw. And in this lecture, we're going to discuss the details of that, how exactly it comes about, and we're going to discuss a kind of a solution called standardization of data. When you standardize data, you kind of remove its dimensionality entirely, so there kind of aren't any units in a way. So we'll talk about the details of this, and we'll do a fair amount of numerical examples trying this out with principal component analysis in R in the second half of the lecture. All right, let's get started. So what we're going to talk about is dimensionless principal component analysis. Dimensionless PCA. And the issue that we're going to encounter today is one that's common in lots of different places in data analysis and in statistics, and it's often overlooked by less experienced people in the field, but sometimes even more experienced people in the field, to pretty horrific effects. So you should keep this in mind. What we're going to talk about is the problem of units. And I'll start off just by giving kind of a simple two-dimensional picture of what this problem actually is. So suppose that we have a simple data set that we were going to do principal component analysis on. And I think we talked about this example data set before. So on the horizontal axis, I'm going to put weight. And this is just art. This is fake data. This is not anything real. And height. Right? And just for sake of argument, suppose that we put the height in units of meters and the weight in units of kilograms. All right, and suppose we're talking about adult men. I think that's where I got some of this rough scale for. So let's suppose that the data kind of lies in the following ranges. So weights tend to be somewhere between, there's a pretty wide range between, say, 40 kilograms and 140 kilograms. Just say roughly speaking, they're in that neighborhood. And let's suppose that height was in the neighborhood of 1.52 meters to 2.03 meters. Right? Seems like sort of reasonable range. And let's just draw some data on here. I'll use orange for that. Maybe I'll use a darker color. We'll go with brown. And let's just suppose that the data looked kind of like this. So that, in some sense, the heavier men tended to be the taller men. But, maybe not always. And so let's say that's how it looked. And then you could kind of draw a little box around this and kind of get a picture for where we are. So this data exists. Oops. Big pen, sorry. So this data kind of exists in this like simple rectangular region in this two-dimensional space. And so this is what we would call normally the data cloud, in this whole region here. And this is a relatively well-behaved one. It seems okay to me. Nothing exciting really going on. And so let's suppose you try to use principal component analysis on this and try to decide which way the principal component axis, the first one at least, would go. And I think that one you can sort of see it would go somewhere like this. Right, so that's what PC1 would look like. And the reasoning for it would be, so it's sort of slanted more towards weight than towards height. I mean, it's some mixture of the two. But so the reasoning for this is the following, that if you look at the variance of all the weights, and you try to compare it to, and so let's say this is around 50 kilograms squared, roughly, just sort of eyeballing that. And you look at the variance of the heights, and this guy is about 0.4 meters squared. Then remember, the way that the principal component analysis axes are chosen is that they're ranked in terms of how large the variances are. So the first axis is the one that has the greatest amount of variance or variation along it, and so on. And so you would look at this and say, well, okay, 50 kilograms squared. Well, we don't really need the squares, but go ahead. Is a lot bigger than 0.4 meters squared, and therefore principal component 1 should be kind of close to weight, right? Because that's the axis that has more variation, and so that's why the tilt of that arrow is kind of closer to horizontal than to vertical, say. Okay, so now let's imagine doing the same thing, but with a different set of units, okay? So let's try some other units, all right? So what if we used different units for heights? What if height was in millimeters? The data is the same, but we just record all the heights in millimeters. And so I'm going to try to draw this set of axes like this. Oops. And you start to, as you draw this, you should start to see kind of the issue. So this is 40, and this was around 140. Oops. And so this was weight in kilograms. And this vertical axis is height, but in millimeters. Height in millimeters. Sorry, bad writing. And you start to see a problem here when you decide, like, well, how do I? Shouldn't this kind of look the same as up here, except just with the numbers being different? So 1.52 meters is 1,520 millimeters. But don't I just relabel that point 1,520 and relabel 2.03 as 2,030? You could do that for sure. But let's just suppose that you tried to keep the axes somewhat on similar scales, so that like a block of, this is something you see students do all the time, they try to insist that like a block of 1 unit on the vertical axis must have the same meaning as 1 unit on the horizontal axis. Of course, that's nonsense, but let's just suppose we tried to sort of honor that. So this bottom number would be like 1,520, and the top number would be 2,030. And the data points, so put them in brown again, they are somewhere scattered in that little box, right? This is not the same cloud, obviously. I'm just making a new set of data points. All right, and then so the box is still it's a little bit different, but you know, it's still defined by these kind of regions here, by those limits. So the cloud is kind of bounded by that box a little bit. And principal component 1 should look something like this. Oops. I want to use a solid line. And what I'm trying to draw here is that it should be a little worse than this. If I tried to make it, you know, this distance here is 100, right? And this distance here is 490. And so that's not, I did not do things to scale. It should have been that this is much, much taller like this. And that would mean that this PC arrow would point more like this. If I tried to make a, you know, every gap of 1 on the paper be the same on both axes, say. But so in any case, though, if the way I've drawn it, the arrow gets tilted a little bit higher up. And, you know, if you go through that same kind of calculation before, you look at the size of the variances, right? So the variance of the weight, that part hasn't changed. Right, so that's around 50 kilograms squared. Again, I'm just making that up. And the variance of the height, this part, it's changed, right? And so now the variance of the height should be 400 millimeters squared. Like that. And so if you went through your decision-making process for deciding, you know, where does principal component 1 go, you look at the variations and you choose, of course, this is just showing the variations along the 2 original axes. You choose axes in different directions, and you try to find the one that has the greatest variation, and you would get something that's, in this instance, closer to something in like the height axis rather than the weight, because 400 is a lot bigger than 50. And so in this case, up above, we had a different result, but so we say, okay, 400 millimeters squared is this time much bigger than 50 kilograms squared. And so P1 is approximately or closer to height than it is to weight. So which one of these analyses is correct? And what's going on? So you should think about this for a second. So the real answer is that neither of these analyses is correct. And here's the fundamental issue here. Hopefully many of you saw it, but maybe not. The fundamental issue here is shown, where do we have it? Here. And also here, right? So what does it mean to say that 50 kilograms is bigger than 0.4 meters? It doesn't even make any sense. A kilogram isn't bigger than a meter. 1 kilogram isn't equal to 1 meter. They're different things entirely. So the idea of trying to make comparisons here between these things is just total nonsense. Like it doesn't make any sense to try to compare these variances because they have completely different units. It doesn't mean anything, right? So the fundamental issue here, the main problem, is that comparing objects with different units makes no sense. Now you could say, well, okay, but it does make sense to compare, like to say that a meter, you could compare it to millimeters because you can convert from millimeters to meters. So like you could say, well, if an object was 2 meters, that's actually small compared to 5,000 millimeters because 5,000 millimeters is 5 meters. But of course, you can't do that kind of thing with kilograms and meters. There's no way to get back and forth between them. So comparing objects with different units makes no sense. And so you can see that there's a real problem with principal component analysis now. It's a significant issue. How do you pick your units from the start? Sometimes you're in a real. Sometimes the problem is so bad, you may not even know what the units are of the data that you're trying to analyze. That's not really, embarrassingly, I have to say, that has come up in some of the projects that I've even assigned, where I say, oh, do something with this data, and I don't even know the units of the data. And that's like a burden that the students have to face. And so this is a real concern. So how do you get around this? And there are, unfortunately, I mean, depending on how you want to look at this, the good news, or it's either good news or bad news. There are ways around it, but there's no like best way necessarily. There are kind of the most common ways, and I'll introduce that way today. And you've probably encountered it before. But so solution. The solution is to make the data dimensionless. Or that's called unitless. That is to say, I mean, really that means picking units, right? But what we want to do is we want to make the units meaningful in some sort of an adaptable way. Make the units meaningful. In some adaptable way. That is to say, I want to have some scheme for how do I choose my units in kilograms, and I want that to be the same scheme for how I choose the units that we're going to replace kilograms, and I want to have that be the same scheme for however it is that I'm going to replace my units of meters or millimeters. And so there's lots of different ways to do that. So one way, I think this is maybe the most naive, simple way, and it turns out it's pretty flawed. And you can think about why that is. Maybe you just do the following. You say, okay, well, everywhere where I had a height in my data record, I'm going to replace that column, all the heights that I had, because they were all in meters or millimeters or whatever. And so I'm going to change them to something better. And so I'm going to change them to, I'm going to change the units to the average height. Right, so everything where there was a height, I'm going to put like, how do you write it? I'll just put average height. All right, so, it's significant if the tallest height is a large number of multiples of the average height. That's interesting, But you can sort of see a flaw with this method, I think. I think you could see, so maybe you don't see it so much with height right away. But there's lots of scenarios where the average of something might actually be close to zero. And so now you would be sort of making all your numbers really big. So that could potentially be a problem. There's other reasons why this might be a problem, but I don't know. You could try it, see what you get. I'll tell you what is a better way, and the kind of more common. It's even in its name, really. So I don't know if this is so much better, but it's certainly much more common, and then therefore seemingly preferred by the masses. And that is to do the following. So you say, okay, I'm going to replace height. All my height numbers are going to be replaced, and what they're going to become, what they'll be replaced with, is height minus the average height. And then divided by the square root of the variance. So maybe I'll just write that standard deviation of height. Right, so that's the square root of the variance of the height. And this method you probably have seen before. This is called standardizing. This is called standardizing the data. And you can see it has an immediately like a leveling effect on the stuff I was doing in the previous example. All of if you try to compute the variation for any of the two axes, height or weight, using the kind of just simple boneheaded picture I was doing here, which was just kind of looking at the range over which they go, they would all give 1. And so you can't just look at the variances for one individual axis and compare it to the other and decide which axis is better. You have to start making these, these different directions and then find out which direction gives you the greater variance. So you can't do it in this kind of boneheaded way that I was just doing. But so this method is super common, and I'm going to say a little bit about how you do it. But really, the way you do it, I think for the most part, the way most of you will do it is you will like turn on some option for standardizing the data, or you'll find some routine that standardizes data and you'll just use it. But you should see kind of how it works, right? So how does it go? So standardizing data, and what are the kind of consequences? Right, so I guess this one should be red. I think I've lost my color scheme going on here. Let's look back at the top. Is anything red? Oh yeah, I did have some things in red. Okay. So standardizing the data. And so here's the idea. So we invent this thing called the standard data, X sub S. And so that's a matrix, and it's row I, column J is going to be the centered data, row I, column J, divided by the square root of the variance, or the standard deviation, of column J of the X matrix. Okay? And so here's standard deviation is just or sigma squared is the variance, the sample variance. So it's 1 over n minus 1. And then this sum down the column k equals 1 to n. And x centered squared row k column j. Right? So that's just the usual definition of the variance. Right? And so let's take a look at what this actually gives us. So sigma, the normal covariance matrix, right? This is just kind of review here. The normal covariance matrix looks like this: 1 over n minus 1, and then x centered transpose x centered, and then if you want to look at row I, column j of that, it just looks like that. And if you go through go back to the original definition and stuff and look at it in detail, it looks like this: 1 over n minus 1 sum down the row, so down the column, k equals 1 to n, and then you have these two different products, right? So xki minus the average of column I times the same thing, xkj minus the average of column j. Right, so this should be very familiar to you at this point. And so the diagonal elements, sigma jj, this is just the squared of lowercase sigma j, right? And so in other words, sigma j is the square root of big sigma jj. So that's a simple way that you can get the standard deviations. You compute the covariance matrix and then take the square root of its diagonal. I think we did that in the first lab, so this is probably very familiar to you. All right, and so we're going to use that to make the standardized data, and we're going to we'll make the standardized data, make x sub s with the following: a matrix called D, which is diagonal, and it's 1 over sigma 1 up to 1 over sigma p. Right, so it's a p by p diagonal matrix with 1 over the standard deviation for each of the columns of the original data. And therefore, Dij is the identity matrix Iij divided by sigma j, right? And if you look at this calculation, so this is going to give you the centered or the standardized data. The standardized data is going to be x centered times the matrix D. And so we'll check that. We'll look at row I, column j. And so this is the method you use to calculate the standardized data. So this is a matrix multiplication. So we get sum over x equals k, sum over k equals 1 to p, sorry about that, of x centered row I, column k, times D, row k, column j. Right, so that's just matrix multiplication. But dkj is really the identity matrix, so that's what this guy is. My writing is really a mess today. More than usual, I feel like. Right, so what that means is it's either 1 if I is equal to j, and it's 0 if not. Right, and so when you put that in here, what that causes, so I'll just write it, why not? Sum over k equals 1 to p. And then divided by sigma j. Right, so what that does is it eliminates the sum, right? So the sum runs until it only picks up the k equal j term, right? And so j is a fixed number, right? It's chosen on the left-hand side of this equation. And so this sum over k goes until you get k equals j, and then that's 1. And so what we get is c times xij over sigma j. Right? And so that tells me it tells me the roadmap. So x standardized is equal to x centered times this diagonal matrix D that's made out of the standard deviations. And I think we computed this in the first practical. I can't remember, but I think I remember us doing that. But that's one way to go it. Okay, and so you use this. So then you use that as the input for PCA. And again, like I was saying, you probably won't ever do that. You probably will instead just give PCA the normal input and turn on some flag for standardizing the data, right? But nevertheless, look what PCA would do, right? So PCA would calculate the covariance matrix. The following covariance matrix, sigma, and then I'll put an S underneath it. And that's 1 over n minus 1 xs transpose times xs, right? And so if you put in this for xs, right, and what we get is the following. So we get 1 over n minus 1. And remember that the transpose of a diagonal matrix is just the diagonal matrix. Nothing changes. Because when you take the transpose, you switch the rows and columns. And the diagonal matrix has nothing on, only things on the diagonal. So there's no, they have the same row and column already. And so we get xc times d transpose times, sorry, that's not, yeah, that's right. And then xc times d, and when you put that together, what you get is d times sigma times d, right? And this thing has a name, right? So this is the correlation matrix. It comes up in, you introduce correlation for the same reason that you introduce this dimensionless principal component analysis. It's that covariance is unit dependent, right? I really kind of can't stress this enough. It's so common that students make mistakes with the relevance of units. For example, I'm sure I will, or Tom Kelsey will, see people submit projects where they report root mean squared errors of some number, but they won't say what that number. They may not even say what its units are, or maybe they'll say what its units are, but what does that mean? You need some context for knowing if that's a big number or a small number, and it's a routine kind of. It's a sign of inexperience for a data analyst to kind of ignore that level of detail. So you want to get on the ball with that sooner rather than later, because you will get on the ball with it soon, at some point. Okay, so again, I'll just write the correlation matrix, and then we'll move on to our code and do our examples, which I think you'll have more fun with. So the correlation matrix looks like this. So it's the covariance matrix divided by sigma I, sigma j, and the name we use for it often is R, right? So that's the correlation matrix. And it's a matrix of what we call Pearson correlation coefficients. All right, so now let's go onto the code. All right, so we're going to try some of these things out and see kind of these principles in action, okay? So the first thing is we're going to load up some data. We'll use another data set from the routine data or from the library data sets. It's called MT cars. It's pretty old-fashioned. MT stands for motor trend. So I just did a help here so you can kind of see it. These cars are from 1974. So it's, real current stuff. And there's a bunch of different columns here. Miles per gallon, cylinders. Motor Trend, I think, is an American magazine, so US gallons. Number of cylinders in the car's engine. The displacement in cubic inches. So again, this is an American magazine. Horsepower. I'm not sure what rear axle ratio means, but the weight of the car. Qsec is the time it takes the car to drive in a quarter-mile race, which is a standard drag race in the United States. And then there's other information here that's really categorical, and so we're going to get rid of. And we probably should get rid of this one as well, number of cylinders, but I'm going to leave it in there just for the heck of it. Okay, so you can read more about the data there. All right, so I'm going to bring it in here and take a look at the pairs plots. This is my EDA for the day here. I mean, I guess in a way the principal component analysis is as well. But so you can see, you just if you squint your eyes and look at these pairs plots, you can see which ones are maybe useful and which ones are maybe not. So like you can see there's trouble actually with the cylinder column because everything is discrete. But then there's a bunch of stuff like in this kind of upper left corner, the first, 6 or 7 items other than cylinders that look promising. So we'll just keep the first 7, I think it is, features and carry on, not worry about the cylinders thing. So we'll drop off that stuff, number of carburetors or whatever that was. That really dates this. And then we'll just do a quick summary to see sort of what things look like. You can see, the scale of the numbers and so on. And I think, in that help file that I looked at the start, it told you what units some of these things were in, so you could make sense of them. Okay, so first let's just do a regular principal component analysis. I'm using the PR comp routine, as I will basically from now on. And we'll do a quick summary on it to see what we get. Okay, so here are the standard deviations. I don't think I printed the matrix of loadings or the rotation, whatever you want to call it. But you can see that, so if you look at cumulative proportion, say, you get in fact, the first principal component would give you 93% of the cumulative proportion of variance. So that's pretty impressive. And not a lot happens going past 2, right? Everything, you're already kind of all the way there. So maybe this, whatever problem you might be interested in, this particular data set could probably be principal componentized into some 2-dimensional data set, and it would be just as good for you, maybe. Okay, so now let's try a different set of units. Okay, so we're going to change horsepower into kilowatts, in case you wanted to know, and I don't know if anybody ever wondered. 1 horsepower is about 3/4 of a kilowatt. So I guess interesting to know. I find it interesting, at least. Of course, a horse does the same amount of energy every second that a kilowatt light bulb does. Who knew that? I don't know. Okay, so we're going to make that change, and that's just scaling this thing. And I'm going to rename the column, just in case anyone wants to look at it, to kilowatts. And then we'll look at the summary again. And that's, so I see that I successfully did that. So the mean is now 38, and it used to be 52. But that's not very different, right? A kilowatt is a horsepower is 3/4 of a kilowatt. So this isn't a dramatic change. But let's do the principal component analysis on it and see what happens. And not a lot changes. So now we get 95% of the cumulative variation just from the first axis. And before we had 93%. So it looks like even more compelling that with this set of units, you could retool this data set into just one feature, and maybe that would contain everything you needed. So if you had a multivariate analysis, maybe you really only needed univariate analysis, if you believe this. But so again, that's not very different. So let's try something with a bigger difference. So the weight was in thousands of pounds, and so we'll change that to grams. And there are many, many grams in 1,000 pounds, almost 500,000. And so we'll do that. So that's a much bigger change. And so here's just the summary. You can see that I successfully changed things to grams. The minimum is 686,000 now. And before the minimum was 1.5. Okay, and so we'll do the principal component analysis and see what we get. And here you get a pretty significant difference, right? So principal component 1 has all information. It's bizarre, right? So you get nothing from any of the other principal components. So maybe what that really means is we just blew up the data. We multiplied one of the columns by 500,000, and that ruined everything, right? And so there's a general rule of thumb for computation that things tend to work better when all the numbers kind of involved in your work are in the same neighborhood. And now we have things that are at like 500,000. And if you look at all these other things, these are 2.8, 14, 71, 30, and nothing else is anywhere near that. So this 500,000 has really blown things out of the water. Okay, so now let's try to use the scaling, right, and see what we get. And so again, we're not going to do it manually. We're just going to turn this thing on scale dot equals true. And the dot matters here. It's almost like begging for a typo and an error. But so we'll do this again, and we'll call the output scaled cars, PCA. And we'll take a look. And here we see a really significant change. So this is using the standardized data. You can look at the help file or even look at the source code to see if it's doing what you expect. But what you see is that the first principal component only contains about 73% of the variation. And so I think you would be a little silly to just use one principal component axis. You probably wouldn't do that. You probably at least would use 2, probably maybe even 3, depending on how much kind of capabilities you had or time on your hands. And so this is a really, really different result, a totally qualitatively different result than if we had not used the scaled data. Now, does that mean that this is the right thing? It's hard to say, I think it's better for sure, because we haven't blown up one of the columns and made it ridiculously big compared to all the others. But, what about these other schemes? Or what if I just divided by the mean? Or there's another thing that's called normalization, which is instead of making the mean 0 and the standard deviation 1, you make it so that the maximum value is 1 and the minimum value is, what do they do, 0? I can't remember. Maybe -1, I've forgotten. But so that's called normalizing. That's another scheme people use. And so you see that there's a problem here, that principal component analysis is sensitive to what you actually do here. So it's not the golden magic wand. There's that quote on the start of the module handbook that says this is not a magic wand. There are many pitfalls. And so this is an example where you start to sort of see that. Okay, so we're going to finish off by doing two different things. We're going to make sure we understand that it indeed is that the rotation matrices and stuff like that do, for the standardized data, look just like the eigenvectors and eigenvalues for the correlation matrix as opposed to the covariance matrix. So we're going to check that. And then we're going to do some actual analysis. We're going to look at some of this principal components and plot the data and see if we can make any sense, or see what kind of analysis we could actually get. Would we be able to learn things about these cars using these funny axes? Okay, so the first thing I'm going to do is just look at the eigenvalues of the correlation matrix. And so that's these. So this is, I compute the correlation matrix by hand, quote, by hand, using the routine correlation matrix. And these are its eigenvalues. And these ought to be those are the square roots of its eigenvalues. So those should be the standard deviations. Do I have those up there? Yeah. So 2.255, that looks right. 1.0754. So all this looks good. To the number of digits shown, we look like we're in pretty good shape. And what about the matrix of loadings? So let's do that. So this is, first I'm just going to spit out the matrix of loadings. So these are the eigenvectors, or the directions of the principal component axes on the original axes. And those should be the eigenvectors of the correlation matrix. And so I'm going to check, see if that's true. And I'm rounding things to 3 digits because it gets tough to eyeball and see, 18 digits or whatever they show you normally. And this looks good, except for one kind of issue that crops up again and again and again, and that is that eigenvectors are only defined up to a sign. So it looks like principal component 1 here points off in some particular direction. And if you look here, if this is principal component 1's direction, it's the opposite of this one, right? So minus 0.413 and 0.413, but that's fine. As long as all the elements have had their signs switched, not like just one of them, then that's fine. It means you've got, one of them had an eigenvector pointed that way and the other one used it this way. That's fine. Okay, and now let's try to look at the unscaled data and see what its eigenvalues and eigenvectors look like. I think we're just going to look at its eigenvectors. So they're pretty different. So this is the unscaled stuff. You could look at that first one maybe. And it's pretty different from the other one. But yeah, again, this is not a big surprise. So what you often do now is you try to have some scheme, and we'll talk a little bit more about this. We'll try to have some scheme for deciding how many principal components do I keep. That's the most common question or thing that students will wonder about. And there isn't really any one rule that everyone must follow, but it's a good idea to have some scheme that you've declared in advance and then kind of go with it and see what you've got. It's also a good idea sometimes to do what other people are doing so that you're not blazing your own trail, but sometimes it's good to blaze your own trail. So sometimes the way people will do that is they'll say okay, I'm going to keep the number of components that's needed so that the cumulative proportion of variance is 90%. And so if I look at these two different cases, the unscaled data, which I think is still using grams, if I remember right, and the scaled data, I get pretty different results, right? So, I don't know, do I get hugely different results? So for sure, with the unscaled data, I would stop after one principal component. And for the scaled data, I probably would keep the first 3 before I got over 90% of the cumulative. So that's pretty different. This person following this rule using standardized data would say, yeah, what we have is a 3-dimensional problem. And if you used the blown up data, you would say one dimension is fine. Okay, so another scheme that people use that's named after this guy called Kaiser's criterion is that you always keep a principal component if its variance is bigger than the average of all of the variances of all of the principal components. And for scaled data, that works out in this really simple way. So you can look at the mathematics here. I'll just say roughly what happens is that for scaled data, what this means is you keep things that have variances larger than 1. That's what this works out to. You can read through that and see that that's the case. And so let's see what this Kaiser's criterion would actually produce for this result. Oh, this is just verifying that the average eigenvalue is in fact 1. Sorry, you'll see that discussed up in that little paragraph. And so let's see what Kaiser's criterion would say. So for the eigenvalues of the correlation matrix, it would say you should keep the first 2. And you don't need these. If you tried to use the unscaled data, and so here I have to manually compute the average of the unscaled variances. And what you get is you should again keep only 1. And so you get a different prediction using this Kaiser's criteria. Another scheme that you could use is, it has a funny name. You could use this plot called a scree plot, SCREE. And what this means is, we actually kind of did this once. You plot the different eigenvalues, and they get smaller as you go further along. And you decide, sort of visually, you're looking for a place where they sort of seem to have leveled out. The name scree plot comes from, I think, it's talking about cliffs, like a mountain cliff. If you've ever seen a really large cliff and gone, hiked up to the bottom of the cliff, what you'll find is a lot of pebbles and broken rocks, things that have fallen off the cliff. And that stuff piles up and makes like a little pile of debris that I think is called scree. And so you have this like sharp cliff and then a gradual low slope decline of scree. And so a scree plot is a name that comes from plotting, looking for a cliff in the eigenvalues and then looking for the debris that you're just going to throw out. And so that's what this is. So we'll do that again for the 2 different cases. So first for I think this is for the non-standardized one. Yeah. And yeah, it's using CAR's PCA. And the next one is for the scaled data, like this. And so it does kind of look like a cliff and then debris. That's the idea. And now this, you can't, I think, depending on how you decide where the debris is, you might not come to a different conclusion looking at this. Is really just a visual version of looking at the size of the eigenvalues, but nevertheless this is called a scree plot, and sometimes it's more obvious than other times. Like I think with this you would say you might say just keep 1, you might say keep 2. Depends on how much work it is for you to keep 2. And then this one, you can at least see that the scree fall off is a little slower for this. But again, this is a visual analysis. Okay, so that's about deciding how you would keep, what number of principal components you would actually keep. Let's try to actually do a little bit of analysis, see if we can use these principal components for something informative. Right, so what we're going to do is we're going to look at the so-called scores. We're going to look at the transform data, and we're going to plot its first 2 axes, which seem like they should be useful. And so the very first thing I'll do is I'll just plot those 2 axes. So in PR comp, the transform data is actually called X, just so you know. That's what we've been calling capital Y in the lectures. So just be aware there's a sort of a notational hazard there. And so this PC1 is going to be column 1 of X, and PC2 is going to be column 2 of X. This is the output for the scaled PCA. And then we'll just make a plot of that. It should be a bunch of dots. Yeah, and so this is PC1 and PC2. And it's sort of uniformly distributed all over the place here. This one has a scale of 4 to 4 roughly, maybe 4 to 3, I don't know, 4 to 4, minus 4 to 4. And this one has a smaller scale, minus 2 to 2. So as expected, the variation along principal component 2 is less than along principal component 1. And so one thing you often do is at this point, you're trying to decide like, well, if I look at these 2 axes, does this give me some way to like discriminate between different sections of the data? So if I label those points with like number of cylinders in the engine or something like that, will I see some pattern? And so that's what we'll do. So I think we're going to use cylinders in the engine first. Yeah, we'll do that. And we'll plot that. And so this is the same data, except each point is now replaced with the number of cylinders in its engine. And sure enough, there's a very clear pattern. The low number of, so the PC1 is small for engines that have a small number of cylinders. There doesn't seem to be any discrimination along PC2 when it comes to numbers of cylinders. So numbers of cylinders seems to be well separated out when you look at principal component 1. And so let's try another one. So we'll use the same two principal components and we'll label them with number of gears in the transmission of the car. And here you see a more interesting spread. So the 3s are in the lower right. Well, there's another 3 over here, but I don't know. So you see it's not as easily, it doesn't as simply separate out the data into groups, but there does seem some separation. The 4s are kind of over in this lower left. The 3s are kind of in the lower right, and the 5s are kind of up along the top. I don't know. You've seen some kind of pattern there. And you can start using more creative and interesting plots. So we'll use a bubble plot. And let's see. So what are we going to do here? We are going to plot. We're going to do 2 different bubble plots. One, so it's the same idea, except instead of plotting a number, the radius of the circle that gets plotted will be given by one of the other axes. So we'll use miles per gallon for the first one. So do that here. And here you can see the result. So large miles per gallon seems to be at low principal component 1. That sort of fits, right, with the low number of cylinders over there. So there's less powerful engines. And so they'll have greater miles per gallon, and less miles per gallon or less efficient engines maybe over here along principal component 2. So we're starting to get a flavor for how you can use principal component analysis to chop up and slice and dice the data and see if it tells you anything interesting. And the last one we'll do is the same, but we'll put weight of the car. And this is back in, I think this is all the way back to thousands of pounds for weight is what's being used here. And you find that the higher weight cars are higher in principal component 1. So maybe somehow principal component 1 might have something to do with like efficiency. So hopefully you now have a better feeling for how units can affect different calculations when you're doing principal component analysis. And hopefully you enjoyed those examples at the end there. In the next lecture, we're going to do 3 more examples. We're going to look at 3 different data sets. See you then.